For decades, we thought we knew everything about our solar system. 8 planets, orbiting neatly around the Sun. But what if I told you there might be a 9th planet lurking far beyond Pluto? A hidden giant shaping the very structure of our cosmic neighborhood. Today, we're diving deep into the fascinating and still highly debated world of Planet 9. We'll explore the compelling evidence that has scientists searching the skies for this elusive world. The first clue that something was amiss came from the observations of Kuiper belt objects, or KBOs. These icy bodies reside far beyond Neptune, and most of them orbit the Sun in a relatively flat plane. But a handful of KBOs, particularly those with highly elliptical orbits, seem to be clumping together. Statistically, this clustering is incredibly unlikely to have happened by chance. It's like a group of runners mysteriously running in the same direction, even when there's no track guiding them. What force could be aligning their paths? The most plausible explanation is a massive unseen planet gravitationally influencing these KBOs. This hypothetical planet, dubbed Planet 9, would be shepherding these objects into their peculiar orbits. Think of it like a cosmic choreographer, guiding a celestial dance. Scientists have run countless computer simulations to test this theory, and the results are pretty compelling. These simulations show that a planet with a mass roughly 5 to 10 times that of Earth, orbiting the Sun at an average distance of 400 to 800 astronomical units, AU, could indeed produce the observed clustering of KBOs. 1 AU is the distance from the Earth to the Sun, so you can imagine how far away that is. But the evidence doesn't stop there. Planet 9's presence could also explain other orbital anomalies in the outer solar system, such as the highly tilted orbits of some KBOs. Again, it points towards a powerful gravitational influence that can't be accounted for by the known planets. So, where is this elusive planet? Well, that's the million-dollar question. Astronomers are using powerful telescopes to scan the predicted region of space, hoping to catch a glimpse of Planet 9. The problem is, at such a vast distance, the planet would be incredibly faint and difficult to detect. Think about it. We're talking about a planet that's potentially 20 times farther away from the Sun than Neptune. The light from the Sun would be incredibly weak out there, making it incredibly faint. Plus, the sheer size of the search area is daunting. The search for Planet 9 is like looking for a needle in a cosmic haystack. Nevertheless, scientists are optimistic, especially with the next-generation telescopes like the Vera C. Rubin Observatory coming online. This observatory's wide field of view will allow it to scan large portions of the sky much faster, significantly increasing our chances of finding Planet 9. Now, it's important to note that the existence of Planet 9 is still a hypothesis. Not everyone is convinced. Some scientists propose alternative explanations for the observed orbital anomalies, such as the combined gravitational effect of a large flattened disk of icy bodies beyond the Kuiper belt. This theory suggests that the slight combined gravitational pull of these icy bodies could mimic the effects of a single, massive planet. While this alternative is possible, it has its own challenges in explaining all the observed anomalies. So, is Planet 9 real? The evidence is intriguing, but the search continues. As telescopes become more powerful and our understanding of the outer solar system deepens, we'll get closer to solving this cosmic mystery. The Sun's corona is its outermost atmosphere. For unknown reasons, it is millions of degrees hotter than the Sun's surface. How is that even possible? That's the coronal heating problem. Let's quickly break down the Sun. At its core, nuclear fusion is happening. generating incredible heat, about 15 million degrees Celsius, 27 million Fahrenheit. That heat radiates outwards. As we move away from the core, things generally get cooler. The visible surface of the Sun, the photosphere, is a relatively cool 5,500 degrees Celsius, around 10,000 Fahrenheit. Makes sense, right? Further from the heat source, less heat. But then, weirdness happens. As we move into the Sun's atmosphere, first through the chromosphere and then into the corona, the temperature skyrockets. The corona reaches temperatures of 1 to 3 million degrees Celsius and can even spike to 10 million degrees during solar flares. Think about it. Imagine sitting next to a campfire, and the air further away from the flames is suddenly way hotter than the fire itself. That's what we're dealing with. It defies intuition, and it's a major headache for solar physicists. Scientists have proposed a few potential solutions. One leading theory is wave heating. The Sun's surface is a seething cauldron of plasma, constantly churning and moving. This movement generates different types of waves, like sound waves or magnetic waves. These waves travel upwards into the corona, carrying energy with them. As they move through the less dense corona, they can be amplified and, importantly, their energy can be converted into heat through a process called wave dissipation. Sort of like how a crashing wave releases its energy on the shore. The tricky part is figuring out exactly how effectively these waves are heating the corona, and if there are enough of them. Also, there are many types of waves, and all of them, if they exist, need to be investigated further. Another compelling theory involves magnetic reconnection. The Sun is incredibly magnetic. Its surface is covered in magnetic field lines that constantly twist, tangle, and rearrange themselves. When these magnetic field lines get too stressed, they can suddenly snap and reconnect in a more stable configuration. This process releases a tremendous amount of energy in the form of heat and kinetic energy, powering solar flares and coronal mass ejections. The energy released during these reconnections could be contributing significantly to heating the corona. The issue is that most of the reconnection events are typically smaller and less frequent than solar flares. The truth is, we don't have a complete answer yet. The coronal heating problem is one of the biggest unsolved puzzles in solar physics. Scientists are using advanced telescopes and spacecraft, like the Parker Solar Probe and Solar Orbiter, to get a closer look at the Sun's corona and try to unravel its secrets. These missions are giving us unprecedented data about the Sun's magnetic field, plasma dynamics, and energy flows. Researchers are also developing sophisticated computer simulations to model the corona and test different heating mechanisms. It's likely that the solution to the coronal heating problem involves a combination of factors, including wave heating, magnetic reconnection, and perhaps even other processes we haven't yet discovered. The Sun's corona remains a fascinating mystery, reminding us that even our closest star still holds many secrets. And solving this puzzle could help us better understand space weather, which can impact our technology here on Earth. The asteroid belt is a region of space between the orbits of Mars and Jupiter. It's filled with millions of rocky and metallic objects, asteroids, also called minor planets. Sizes range from pebbles to Ceres, which is so big it's classified as a dwarf planet. Don't picture it like a dense field from Star Wars. Asteroids are widely spaced. If you were on an asteroid, you'd be unlikely to see another one with the naked eye. But despite the space, the belt is there, and it's one of the biggest mysteries in the solar system. So, why isn't there a planet between Mars and Jupiter? The most common and initially logical explanation was the missing planet hypothesis. The idea was that a planet did start to form there, accumulating dust and gas like the other planets. The problem? Jupiter. This gas giant is massive, way bigger than all the other planets combined. Its immense gravity had a disruptive effect on the asteroid belt. Instead of allowing the planetesimals, the building blocks of planets, to gently collide and stick together, Jupiter stirred things up. Collisions became more violent, shattering objects instead of allowing them to merge. Jupiter basically slammed the brakes on planet formation in that region, and eventually flung most of the material out of the solar system or into the Sun. This is the most popular theory, but it doesn't explain everything. Here's where the mystery deepens. The total mass of all the asteroids in the belt is only about 4% of the Moon's mass. That's not nearly enough material to have formed a planet, even a small one. So, even if Jupiter hadn't interfered, it's unlikely a planet could have fully formed there with so little stuff. Some scientists suggest that the asteroid belt might have originally contained much more material, perhaps equivalent to the mass of Earth. If that's true, then some other process ejected 99.9% of the original mass. One compelling idea is the Grand Tack hypothesis. This theory suggests that Jupiter didn't form in its current location. Instead, it migrated inwards towards the Sun, disrupting the orbits of planetesimals in the inner solar system, including those in the asteroid belt region. Then, Saturn caught up, and the two planets migrated back outwards to their current positions. This tack maneuver could explain why the asteroid belt is made up of a mix of materials from different parts of the solar system, as well as why it's so depleted in mass. But even the Grand Tack doesn't solve everything. There are still unanswered questions about the different types of asteroids, their compositions, and their orbital characteristics. Some asteroids seem to have formed much farther out in the solar system and were later scattered into the belt. Others seem to be remnants of the original protoplanetary disk. Figuring out the precise origins and evolution of the asteroid belt is like piecing together a cosmic puzzle with many missing pieces. Thankfully, we're not giving up. Space agencies like NASA and JAXA are sending missions to study asteroids up close. The OSIRIS-REx mission successfully collected a sample from asteroid Bennu, and the Hayabusa 2 mission brought back samples from asteroid Ryugu. And the upcoming Psyche mission will explore a metal-rich asteroid that could be the exposed core of a protoplanet. By analyzing these samples and studying asteroids in detail, we're hoping to find more clues about the formation of the solar system and, of course, the enigma of the asteroid belt. The Kuiper belt is a vast region beyond Neptune, a swirling disk of icy bodies, remnants from the formation of our solar system about 4.6 billion years ago. Think of it as a cosmic construction site filled with leftover bricks and debris that never quite made it into a planet. It's home to dwarf planets like Pluto, Eris, Makemake, and Haumea, and countless smaller objects. We call these Kuiper belt objects, or KBOs. They are essentially icy rocks, frozen relics of the early solar system. Studying the Kuiper belt helps us understand how our system of planets formed in the first place. Scientists estimate that the Kuiper belt contains hundreds of thousands of objects larger than 100 kilometers across, and trillions of smaller ones. That's a lot of potential data for planetary scientists. Now, here's where things get really interesting. When astronomers started mapping the Kuiper belt, something strange popped up. We expected to keep finding KBOs as we looked further out. Instead, at around 50 astronomical units, AU, from the Sun, that's 50 times the distance between the Earth and the Sun, the number of KBOs plummeted. This sharp drop-off is what scientists call the Kuiper cliff. It's like the universe just decided to stop creating objects beyond that point. It's as if something swept the area clean. But what could it be? This is where the fun begins, because no one really knows for sure. But there are some compelling theories floating around. Theory 1, a passing star. Imagine a rogue star hurtling through space and passing close to our solar system billions of years ago. Its gravitational pull could have scattered the outer KBOs, flinging them out of the solar system entirely, leaving a void beyond the cliff. Theory 2, a lost planet. Some scientists hypothesize that there might have been a large undiscovered planet, perhaps even a Neptune-sized planetary body, in the outer reaches of the solar system that swept up some of the materials and cleaned that region. Over millions of years, it could have gravitationally sculpted the Kuiper belt, creating the cliff we see today. This is linked to the Planet 9 hypothesis. There could be a planet out here that affected the belt's shape. Theory 3, the combined effects of many smaller objects. It's possible that the cliff is not the result of any single factor, but the combination of gravitational effects and collisions over billions of years. Small interactions and gravitational forces that cleaned it out over a long period of time. What's great about science is that all the theories are tested, debated, and questioned until we can get a suitable answer. The Kuiper cliff remains one of the biggest mysteries of our solar system. To solve it, we need to explore the outer reaches firsthand. Future missions are planned to get a closer look at the objects that do exist beyond the cliff and to map the region in greater detail. As technology advances, we'll be able to find more objects that lie beyond the cliff. Future telescopes and probes will give us more information as we gather more data. Who knows what secrets the Kuiper belt holds? Perhaps the Kuiper cliff is a clue to the existence of Planet 9. Or maybe it's just a reminder that our solar system is far more complex and dynamic than we ever imagined. So what is the Oort cloud? Think of it as the solar system's attic, a vast spherical shell of icy leftovers from the formation of our planets. It's so far away, we've never even seen it directly, which makes it all the more fascinating. Imagine the Sun at the center, then the planets, the asteroid belt, the Kuiper belt with Pluto and all its icy friends. Now, keep going, and going, and going. We're talking distances thousands of times farther than Pluto. The Oort cloud is a theoretical sphere surrounding our solar system, made up of trillions, yes, trillions, of icy objects. Think of them as dirty snowballs, remnants from the early days of the solar system's formation, about 4.6 billion years ago. These objects are mostly made of ice, water ice, methane ice, ammonia ice, mixed with dust and rock. They're spread incredibly far apart. Think of it like a few grains of sand scattered across a football stadium. Space out there is vast. The Oort cloud is theorized to extend from about 2,000 to 200,000 astronomical units from the Sun. 1 AU is the distance between the Earth and the Sun. So, yeah, huge! So, how did all these icy objects end up so far away? Well, when the planets were forming, there was a lot of gravitational chaos going on. The giant planets, especially Jupiter and Saturn, acted like cosmic bullies, flinging smaller icy bodies outwards. These icy objects were originally much closer to the Sun, in the same region where the planets formed. But close encounters with these massive planets sent them careening outwards. Some were ejected from the solar system entirely, but many were nudged into highly elliptical orbits that took them to the very edge of the Sun's gravitational influence. Host. It's like a cosmic game of pinball, with the planets acting as the bumpers, sending these icy balls flying into the outer reaches of space, where the pull of other stars began to affect them. Now, here's where it gets really interesting. Comets. The Oort cloud is believed to be the source of long-period comets. Those comets with orbital periods of hundreds, thousands, or even millions of years. These comets are dislodged from their distant orbits in the Oort cloud by gravitational disturbances. This could be from a passing star, the gravitational pull of the galactic tide, or even interactions with giant molecular clouds. Imagine a passing star nudging one of these icy objects, changing its orbit just enough to send it plummeting towards the inner solar system. As it gets closer to the Sun, the ice and dust on its surface begin to vaporize, creating that beautiful tail we see from Earth. Not all comets come from the Oort cloud, some come from the Kuiper belt, but long-period comets, those with really long orbits, are thought to be Oort cloud originals. So, why should we care about this distant icy realm? Well, the Oort cloud holds valuable clues about the formation of our solar system. Because these objects have been preserved in the deep freeze of space, they're like time capsules from the early days. By studying comets that originate from the Oort cloud, we can learn about the composition of the protoplanetary disk from which our solar system formed. This helps us understand how planets form and, potentially, how life might arise on other planets. Also, the Oort cloud poses a potential threat. A large object dislodged from the Oort cloud could, theoretically, impact Earth. While the chances are extremely low, it's a reminder that our solar system is a dynamic place and that we need to understand the potential hazards. The biggest challenge with the Oort cloud is its immense distance. We've never directly observed it, and it's unlikely we'll be able to anytime soon with current technology. The objects are too small and too far away to be seen with our telescopes. The biggest challenge with the Oort cloud is its immense distance. We've never directly observed it, and it's unlikely we'll be able to anytime soon with current technology. The objects are too small and too far away to be seen with our telescopes. However, scientists are working on new technologies and mission concepts that could potentially allow us to study the Oort cloud in the future. Imagine a spacecraft equipped with advanced telescopes and sensors, venturing out to the edge of our solar system to directly sample Oort cloud objects. It would take centuries to get there, but the scientific payoff could be enormous. The Oort cloud, a vast and mysterious realm at the edge of our solar system, is a reminder of the incredible scale of the universe and the ongoing quest to understand our place within it.